All right. So we've spent a lot of time talking about how we model heat transfer that happens between two different objects. We created that equation, Q double prime is equal to H times delta T, as a way to try to understand how heat transfer between two objects takes place in a quantifiable sense. And then we use that equation to try to understand how we can obtain meaningful variables about the heat transfer that occurs between the human body and the environment around us. And so now the question that we have to ask ourselves is that model enough, right? Is Q double prime equal to H times delta T enough? And the answer is no. And to be able to understand why that answer is no, it's helpful for us to revisit the way that we usually set up systems using the kind of H delta T paradigm, and then interrogate them and see whether or not there's some kind of like conceptual issue with trying to apply the equation, in particular when we are trying to understand the heat transfer that occurs inside of the object rather than between an object and something else, okay? So if I take some cube and immerse it in environment, right? Let's suppose that this environment has some temperature T infinity, and that, I don't know, some random point on the surface of the cube has temperature Ts, all right? We might ask ourselves, well, given this setup, what is the heat flux that's occurring between this little section of the boundary between the cube and the environment? What is the heat flux that's occurring at that point on the boundary? Well, the magnitude of it is pretty simple. You can just quantify it as Q double prime is equal to H delta T, like we talked about before. Now, one of the questions that we had to ask ourselves was, well, what is the delta T? Is it the temperature of the environment minus the temperature of the surface, or the temperature of the surface minus the temperature of the environment? And the answer to that is that it actually depends. Because usually when we talk about heat fluxes, we have to talk about directions. We have to talk about heat transfer rates, but from what to what? From the perspective of this, we can ask questions like, what is the heat transfer rate that's occurring from the cube to the environment? And by extension, we can ask ourselves, what is the heat flux that is occurring at this specific point between the cube and the environment? And this setup, that phrasing from the cube to the environment implies something about signs here, okay? If it turns out that, for example, I'm considering how much is going from the cube to the environment, then we are considering heat transfer that's occurring outwards, which only happens if the temperature of this point Ts is larger than T infinity, okay? And so we would define in this scenario the delta T to be Ts minus T infinity. Why? Because when this is positive, assuming, of course, that the heat transfer coefficient is positive, which we always will. And so our definition of delta T has to be consistent with whatever the conceptual phrasing we're using for describing heat transfer between these objects. Okay? If we're saying heat transfer from the object to the environment, then we define our delta T this way, such that the heat flux is positive whenever heat is actually being transferred out to the environment, right? Which only happens when Ts is larger than T infinity. Now, this is all well and good, right? So we don't have to worry about thinking about like directions, like in which direction is this heat flux going, because we know conceptually in which direction it's going outside, right? It's very easy for us, if we can clearly partition this cube and the surrounding atmosphere, if we can make a clear partition between them, which clearly we can, it seems very obvious that in the physical scenario that we were just describing, heat flux is going outwards in this direction. If we had been considering, for example, heat transfer here, and the heat transfer was still happening outwards, right? So the temperature of this point is still larger than the atmosphere, then the outwards direction is still easily defined. It's just perpendicular to this surface, And so we never have to spend too much time thinking about, oh, what is the direction of the heat transfer, because we can pull it out very quickly from the geometry, and also just an understanding of in which, is the heat transfer happening from this object to this object, or from this object to this object at that point, okay? And this will wind up being a problem, not for exercises like this, but for whenever we start to ask ourselves questions like, what is the heat transfer that's happening at this point on the inside of this cube? Okay? This point, although I can't physically draw it, is located inside. It's surrounded by more material of whatever the cube is made out of. Okay? So there's no environment, there's no T infinity. In which direction is the Q double prime pointing? Right? And if I tried to do an analysis where I said, okay, well, let me just think about, I have this point, I'm going to create like a little region around the point, and then try to, use the same logic we did before, that's not really going to work, because the region is a point. It has no surface area, it has no volume. And in particular, it's not going to have a well-defined out or in, okay? Because it's just a point. There's no volume to it. There's no inside or outside. Well, technically everything is outside, right? You can't define these things consistently. And so we have to try to come up with some other equation that not only will tell us about the direction of heat transfer that occurs inside of points that are not on the boundary of two objects, but also accounts for something else. Think about the way that temperature changes inside of an object. You really don't expect temperature to discontinuously switch from one value to another inside of a single physical object. Like, you don't expect the temperature of one piece of this thing to just be 20 degrees Celsius and then have it suddenly jump to 100. Even though you can expect drastic changes, usually those changes happen continuously. That is to say that it will take some space, that it will grow. Before it hits 100, it has to hit 30 and 45 and 60 and so on and so forth, even if it's happening over a very small region of space. And this is also a problem, because it means that the temperature of all of the points that are surrounding this point, if that temperature field is continuous, are also going to be the same temperature as the point. Okay? And so if we try to say, well, the delta T that we're using to quantify Q double prime is just the temperature of the surrounding points, or maybe the average or something like that, that's not going to work either, because the temperature of the surrounding points is going to be infinitesimally close to the temperature of the point. And so this equation fails, both because it's not giving us any information about direction for points inside of a system, but also because it's not giving us any information about how we model the heat flux that's happening around points that are roughly the same temperature. Okay, so inside of media. So how do we do this? Well, the natural question that we should ask ourselves is to try to find some other physical quantity that will allow us to do so. Right, so maybe Q double prime being a function of delta T is not the right answer for modeling heat transfer inside of objects. Maybe it has to be a function of something else. What that function is, we'll determine in a second. And to analyze this, let's go to another system. Let's just consider like a slab. Okay? And we can imagine that this slab has maybe temperature T1 on one side and temperature T2 on the other. And that the temperature transitions continuously between T1 and T2 inside of this wall. Now, for the sake of just making a graph, we're going to say that T2 is larger than T1. Okay? And if we draw the graph, making sure that I get it on camera, yep. If I make a graph, where I'm going to define a variable x such that x is 0 on the left side of the slab and some positive value on the right side, right? That it increases as you go left to right. If I were to plot this temperature, you might expect to see something, who knows? It could be all kinds of different things. We don't know anything about like what's happening in the slab yet, but we know that it can be something like this. Okay, whatever. Or I guess to make it to scale, there we go. That's better. And so we may ask ourselves something like, what's happening, I don't know, at this point right over here? Like what is the heat flux that is located at this point? And we're not going to care about other dimensions in space. We're only going to care about x for now, just to make it easier on our brains. And how do we determine that based off of the fact that the temperature around this point is going to be very, very similar to the temperature of the points around this is going to be basically the same as the temperature of this point. How do we do it? Well, we need to use information that tells us stuff about how temperature changes that isn't necessarily directly delta T's, right? And so what is the piece of information that makes sense for us to use here? Well, the piece of information that makes sense for us to use is to see how much that temperature changes as a function of time. As a function of space. Okay? To write a derivative, dt dx, that tells me information about how much the temperature increases as I change x, and then use this information as the key quantity that tells me what the q double prime is. Okay? And so now, the heat flux that we're looking at here is not going to be a function of delta T, it's going to be a function of dt dx. Because this is something that we can very, very clearly define for this point, and it's something that we can define for every other point too. Okay? It's something that makes sense for us to define as something that changes with x the same way that the temperature changes with x. So, now that we created this idea, this hypothesis, we can then ask ourselves, well, how does this work? Well, notice that this should behave in very much the same way that q double prime is equal to h times delta t should behave, at least in the sense that whatever the governing equation of this thing, whatever this f is, it should behave a lot like what this f was. Why? Because dt dx, whenever this is 0, right, whenever there's no local change in the temperature with respect to space, then we would expect heat transfer to not occur. We would expect the heat flux to be 0, because temperatures, at least surrounding the neighborhood of the point, are in that instant going to be, those temperatures are all going to be the same around the neighborhood of the point, which means that there should be no heat transfer taking place, at least at that instant in time, okay, and in that location in space. So we have basically the same setup, and you can kind of see where we're going with this. It doesn't matter what this function is if we assume that the laws of physics that we're using to create this equation are operating in regimes, like all the experimental data that we pull is for regimes where dt dx is very, very small, whatever that means, then it turns out that we can replace this with something that is proportional directly to dt dx multiplied by some constant. Now there's two different subtleties that we have to consider when it comes to understanding what goes here. Okay, the first is that the units of dt dx are not the same as the units of delta t. And what that winds up meaning is that whatever this constant is, it's not going to have the same units as the constant that we saw before, okay, as the heat transfer coefficient. The coefficient that's going to show up here will have different units, and as a result, we think of it as a different thing, and we call it a thermal conductivity K. So let me write this down over here to make it clear that we have now created basically this other fundamental property that we need to consider in the study of heat transfer, which is the thermal conductivity K. All right? And this thermal conductivity, instead of having units of watts per meter squared degree Celsius, this now, because it already has this factor of dt dx, it has units of watts per meter squared divided by something that has units of degree Celsius per meter. And that means that thermal conductivities have units, at least in the international system, of watts per meter degree Celsius or watts per meter Kelvin. Doesn't matter too much. And so ultimately, we classify this as being a different quantity, even though it comes up from the same place, right? It's just a fudge factor that we pull from experiments in order to be able to understand how we relate q double prime to dt dx. You take some material, you generate a dt dx through it, you measure the q double prime, and then you estimate the k based off of that, right? And that k is subject to the exact same weird whims that the h was, right? It can be a function of anything. Now, usually k's tend to be controllable in a much more strict sense than h's, because h is something that is a property of two different objects, right? And there's all kinds of combinations of two different objects you can put together, whereas the thermal conductivity is usually studied inside of a single kind of object. And so thermal conductivities are usually assumed to be material properties, even though technically speaking, they're not. Usually they tend to be material properties because they're only a function of the single material that we're studying heat transfer inside of, right? Of the single object that we're considering. So yeah. But that being said, that doesn't mean that the thermal conductivity can't be a function of a bunch of different things, right? Thermal conductivity is a function of temperature. It's a function of all kinds of like weirdly unrelated material properties that you would think don't affect it, but do, right? And so it's the same, weird thing. We're not going to have a nice theoretical mechanism to pull what K is from first principles. We just measure it from experiment and say, off we go. So we're just going to say that this thing is approximately a material property, okay? So we've derived this other, okay. Is this the end of the story? Well, this was the end of the story whenever we were doing modeling heat transfer between objects, but there's something that's kind of missing here. Technically two things, okay? The first thing is, in which direction is the heat transfer happening, okay? So remember, we drew a graph. We had drawn a graph where, although it doesn't exactly matter, we had assumed that heat transfer that the temperature increased from one side of the wall to the other in this like weird, goofy way. And if I wanted to analyze the heat transfer, say like over here, well, I have to analyze what the value of this dt dx is. But because I've defined a specific value of x, that it matters whether or not we define the x to go up this way or this way. Why? Well, think about the direction in which heat transfer occurs in this point, just based off physical intuition. Okay, so if we operate under the assumption that heat transfer happens from hot to cold, if the temperature goes up, right, if this dt dx is positive, which it is in this graph, then you would expect that the heat flux is actually happening in this direction, right? So in the negative x direction. And so the way that we account for this is that we basically say, okay, well, this quantity that we're calculating here is actually the heat flux that is happening in the x direction. And we have to attach a negative sign to account for that physical behavior where whenever temperatures increase in the direction of x, dt dx will be positive, and because heat flux goes from hot to cold, right? Heat is transferred from hot things to cold things, the heat transfer will always oppose the direction of dt dx. And you can do this argument in your head if you imagine that the curve was decreasing at this point, and you'd find the exact same thing, right? So we have to attach this negative sign in order to be physically consistent, and in order to keep these k's positive. One thing that we could have done was just to make the k's negative, but, you know, easier to just keep the k's as being positive material properties and then just attach the minus sign on the outside, okay? And the thing that I can do is that for every direction, right? So we did this for a system that was one-dimensional, right? Where we only considered things in the x direction. But we can also consider an argument where we try to find the q double prime that's happening in the y direction at that point, okay? And using the same argument and the same logic, we wind up finding an equation that will look like this. Now, technically speaking, these coefficients could be different. So I'll just put a subscript there, right? So these thermal conductivities might be different. We'll usually assume them not to be, but we'll get to that in a second. And then the exact same thing over here. Right? So we can rotate, you know, we can define our different directions and then construct equations that tell us what the heat flux is in those directions as a function of the rate of change of the temperature in space in those directions multiplied by this thermal conductivity multiplied by a minus sign. Now, most of the time, we don't have to worry about these subscripts. Most of the time, materials are such that, you know, when you zoom in to a specific point, you don't observe that there's any like weird properties of the material at a, you know, molecular structural level. And so it doesn't really matter in which direction the heat transfer is taking place. You assume that the structure is kind of isotropic, that it doesn't vary or change depending on which direction you are looking in, okay? But there are some materials in which that happens. And so in those materials, you would expect to have different thermal conductivities in different directions, all right? But for the purposes of what we're going to be doing for the rest of the course, we're just going to assume that the K is constant, that it doesn't change as a function of X or Y or Z, that it's not dependent on which orientation you choose to put the material in, like there's no weird microstructure, okay? And so this is giving us information about what the heat flux is in specific directions. And so if you are already familiar with vector calculus or vector mathematics, you'll notice that this looks like I've created the components of a vector, and that's exactly true. And so what's happened is that I've come up with an expression that tells me what the components of the heat flux vector are in these three different directions. And so I can use this to write down something that tells me explicitly what that vector is, right? So rather than writing down the components, I can actually write down the full-blown vector. And what we're going to wind up getting when we combine everything through is that q double prime, and we're attaching a little vector arrow to symbolize that this is actually a vector, is equal to minus k times the gradient of the temperature. So at a specific point, the heat flux vector, both the magnitude and the direction, are determined by the thermal conductivity and the temperature gradient at that specific point. And if you're wondering what the temperature gradient is, if you're wondering what a gradient is even, it's just a vector that at a specific point takes its partial derivatives and then provides information about how much that quantity changes in the directions that you've defined for your coordinate system. So in a standard XYZ Cartesian coordinate system, the gradient of the temperature is just going to be the rate of change of the temperature with respect to x in the x direction, so multiplied by a unit vector in the x direction, plus the rate of change of the temperature in the y direction, multiplied by the y unit vector, and you get the idea. And so depending on the coordinate system that we use, this expression will look different, right? So if I was using cylindrical or polar coordinate systems, I'd find that the expression that I get is different because my directions are different. Makes sense. But the point is that we can create a model for understanding how heat transfer occurs inside of objects that gives me everything that I wanted, right? It's giving me a magnitude. It is not a function of explicit temperature differences. It's a function of temperature gradients. And it provides me with a direction immediately, right? So this satisfies everything that we want for modeling heat transfer that happens inside of objects. And the crazy thing about this is that there is no new physics, right? All that we've done is we've basically said, well, it turns out that, the H wasn't cutting it because what happens with the delta T's. So what I'm actually going to wind up doing is I'm just going to go and say, well, forget delta T. Now let's consider a temperature gradient. And if I consider a temperature gradient, and I just make the same assumptions that I did when I was trying to derive the H times delta T equation, I just wind up getting this linear equation that relates delta T to Q double prime by some just linear constant fudge factor K that we pull from experiments, all right? And that negative is just there to accommodate the fact that this is a vector equation. So once again, we haven't uncovered any new physics, okay? This is just a mathematical model where we've tried to create the simplest equation possible and then just jammed all of the stuff that we don't know or like into the K, all right? And so now what we have to consider is, okay, now that we've described how heat transfer occurs inside of objects, now that we've created this new equation to describe it, how can we use it, right? In the same way that we used the equation of Q double prime is equal to H times delta T to model heat transfer between two different objects. And what you'll find is that this is often used for modeling conduction, right? So when I have a solid object or two solid objects that are in connection, this equation is the equation that is most often used to model that particular type of setup of thermal conduction, right? There's a reason this is called thermal conductivity. And we'll see that in an exercise, in a couple of exercises, in the next few lectures. All right.